Hi everyone, here is our EACL 2024 paper, Localization versus Semantics, Visual Representations in Unimodal and Multimodal Models. This is joint work with Zhuowan, Ben, and Ellen. In the past 2 years, pre-training with multimodal data like vision and language has been shown to be effective on a wide range of tasks. Representative multimodal large models include CLSP, which is a contrastively trained model using image and text pairs, and Alpha, which is a generative model trained by masked modeling losses. In this work, we are interested in studying and diagnosing the visual features in these models. We try to answer this question: how good are the visual features in multimodal models, especially in comparison with single modality models pre-trained with visual data only? We study the feature quality through feature probing. Specifically, we first extract features using the pre-trained models, then train a simple, lightweight network head to predict the output for a series of probing tasks that I will introduce in the next couple of slides. Note that during the probing, the features and the pre-trained models are kept frozen, and the only trainable part is the lightweight probing head. In this way, we can access the information that is explicitly encoded in the features. Using feature probing, we compare two types of models, including vision and language models like CLSP, Alpha, Flava, and vision-only models like MAE, masked autoencoders, and MoCo v3. Here is the list of the 5 probing tasks that we are interested in. Some tasks focus on semantics while the others focuses on localization. The first task, object prediction, requires a model predicting the name of the object in the given bounding box, a panda in this case. The second task, attribute prediction. It is similar to object prediction. The difference is that now it requires a model to predict the attributes for the objects in the bounding box. In this case, a panda is black and white, is furry, and etc. The third task, object detection, requires a model to detect the object from the images, which is to predict both the bounding box location and also the name of the object. To predict the bounding box location, more localization information is required. The next task, instance segmentation, requires segmenting the object from the image, which focus more on localization because it requires segmenting the boundaries of the object. And the last task, part segmentation. This is a more fine-grained localization task that requires segmenting different parts of the objects. In this case, the head, the body, and the arms of this panda. In summary, we compare these two types of models, vision and language models, and vision-only models on these 5 tasks. The first 2 tasks focus on label, object name, and attribute predictions. They are label prediction tasks that requires more semantic information, and the last 3 tasks requires more localization information. We want to discover the characteristics of each model on these different aspects. Here is a list of more details about the datasets, the evaluation metrics, and the probing heads for each of the 5 tasks. Here comes our major results. We probe these 5 models belonging to 2 categories on these 5 tasks. The 5 probing tasks, including 2 semantic tasks as shown on the left and 3 localization tasks as shown on the right. The higher the numbers, the taller the bars means the better performance. So now let's get some findings by looking into the bars one by one. First, vision and language models are stronger on semantic tasks. As we can show on the left 2 tasks, name prediction and attribute prediction, The vision and language models perform better than vision-only models on these two tasks, indicating that their features encode better semantics. However, differently, on the other three tasks that requires more localized, dense predictions, vision-only models are better. As shown here, on these three tasks, object detection, object segmentation, and part segmentation, vision-only models are stronger than vision and language models. So our finding number 2 is that vision-only models are stronger on localization. Now let's take a closer look into the segmentation results to further separate localization and semantics. Since the segmentation task requires both segmenting the boundaries of the object and also labeling them, we can evaluate the mask and the label prediction separately so that localization and semantics can be fully disentangled. To evaluate localization only, we merge all the regions for different categories into one single region so that the prediction segmentation mask is transformed into this binary mask, and then we can evaluate the shape of this binary mask only to represent localization results. To evaluate semantics only, we transform the prediction into a set of labels like head, body, and arms, and then we can evaluate the accuracy of the predicted labels only. Here is the decomposed evaluation results. For the overall results like MAP and MLU as shown here, vision-only model like MAE is the best. However, if we look at the decomposed semantic and localization results separately, we can see that vision and language models are actually much better on the semantic side, which means that they predict the labels better than the vision-only models. The advantage of vision-only models mainly come from stronger localization. To understand this better, here are several examples. The first column is the image, and the second column is the ground truth segmentation results for the image. Different colors here in the mask represent different labels of the region. As we can see, the vision-only model predictions are mostly accurate on the shape boundaries, like the curly shape of the snake and the fins of the shark. However, the labels are not fully correct. For example, MAE here misclassifies the shark fin as the reptile feet. In contrast, as on the right, vision language models predict mostly correct on the labels, but they are not very accurate on the shape boundaries. Here, let's take another close look to the attribute prediction results. We categorize all the attributes into 8 categories as shown here, like actions, textures, shapes, sizes, colors, materials, states, and the others. We can see that vision and language models predict attributes better on almost every category. However, if we look into the results in more detail, we can see that the gaps are much larger on more abstract attributes, like actions here on the top. The gap here is much larger than the more lower level attributes like textures. Since to understand different actions, the model needs to have a more abstract understanding of the image, while to understand textures, it requires more localized, low-level understanding. So this result also suggests that vision and language models are much better than the more abstract label prediction tasks. We also run some ablations on different model sizes and fine-tuning tasks. Please check out our paper for more details. To summarize, we probe the vision language models and vision-only models on 5 different tasks, ranging from semantic tasks to localization tasks. Our probing results suggest that vision and language models are stronger on semantics, but they are not stronger on localization. We hope our work can be an initial step to study the role of language in visual learning. We suggest that language can help visual models to learn better semantics, and we are looking forward to seeing more works to explore in this direction. We also hope that our probing results can be an empirical guide for future researchers to choose which foundation models to use. Thank you for listening.